guys, it's me Shireen, and this video is on gas density and partial pressures.
So hello everyone, today we'll talk about gas density and partial pressures. Remember the ideal gas law, P equals nRT over V, or PV equal nRT, and the combined gas law, which shows that P1V1 over N1T1 equal P2V2 over N2T2. Let's look at first problem here where 210 liters of this oxygen gas at STP is raised up to 100 Celsius, and we're trying to find out the new pressure P2. For this we'll use the combined gas law. Notice we're in one condition, we have another condition, so we'll realize that V1 is equal to V2 here, and N1 equally N2, no change in volume or change in number of particles. Removing those, we get this nice simple expression here, and putting in our values for the pressures, and make sure the temperatures are in Kelvin. We'll use 273 plus 100 to turn 100 Celsius into Kelvin, and we can easily work out here that the new pressure, after checking the units, is 1.37 atmospheres. So in the second problem here, we're asked about the mass of chlorine in a 200 liter sample at 3 atmospheres. This is just an ideal gas law problem, and we'll solve for the number of moles and then convert that to mass. So solving for N here and putting in the correct values from above, and also use the R is equal to 0.0821 version because we're in atmospheres. And to make sure you convert those 15 degrees Celsius into Kelvin, check all the units, we wind up with moles, and that winds up as 25.38 moles of that chlorine gas. We're not quite done yet, we're looking for the mass, so we'll just convert these moles of chlorine gas into mass here using the molar mass of chlorine gas as 71 grams per mole. This gets us 1802 grams, or since we only have two significant digits here, 1.8 by 10 to the 3 grams of chlorine gas. Here's one more sample problem. This one here has got some stoichiometry in it. We're going to react some magnesium metal with excess sulfuric acid. So first let's get the balanced chemical reaction. Remember that these reactions between most metals and acids release hydrogen gas and a salt, in this case magnesium sulfate and hydrogen gas. So a little stoichiometry here, we'll start with the 12.2 grams of magnesium, use its molar mass, and then we'll use the mole ratio between the mole of magnesium and the mole of hydrogen gas. Checking all the units, we wind up with moles of hydrogen here at 0.5021 moles. We won't round now, we'll keep rounding for later on. So back now to the ideal gas law, solving for V is equal to nRT over P here, and we'll just put in the values. There's our 0.5021 moles from above, and here we have our 0.0821, that'll be our ideal gas constant using atmospheres, and here convert the Celsius to Kelvin, and remember it's 2.25 atmospheres to the pressure, and this turns out, as quickly checking all the units, 6.56 liters of hydrogen gas. So there's a quick review of how to use the combined gas law and ideal gas law. Now let's get on to our actual topic for today, which is gas density and partial pressures. So let's have a look at those. First thing we'd like to talk about is these things we call partial pressures. And that's got to do with this idea that when you take a bunch of gases and put them in a container, that they'll have a total pressure equal to the pressure contributions made by each of the different constituents of the gas mixture. So once again, the total pressure of a mixture of gases is equal to the sum of pressures of the contributions from each gas in a mixture. As it turns out, the pressure contributions are equal to the mole ratios, or the mole fraction, of the gas in the sample multiplied by the total pressure. This is not something we dive into too deeply in this course, but it will come up in future courses, and it's worthwhile knowing Dalton's law of partial pressure. Okay, that's it. P total equal P1 plus P2 and P3. Now let's talk about gas density. And you might remember that density is mass over volume. And so if you don't mind, we'll just make mass here into number of moles times molar mass and divide that one by volume. So here's a new symbol, this large curly M. Molar mass is grams per mole, and of course number of moles we have is N, and the volume is in liters. So if we do that, we get density equals little n times big curly M divided by volume. I'll separate N over V here because if you notice on the side, that N over V is also equal to P over RT from the ideal gas law. Substituting that one in, we wind up with this D is equal to PM over RT, or the density of an ideal gas in grams per liter is the pressure in kilopascals or atmospheres, depending which R value you use. And R here is the ideal gas constant. Use the correct version, depending on kilopascals or atmospheres. Never forget that one. And finally, the temperature here will be in Kelvin. So this is the density of an ideal gas. Okay, it's quite useful as it is. It's helpful to be able to work out the density of an ideal gas. But we can even rearrange it further, and we'll rearrange it into this form where the density is equal to PM over RT, and we'll fiddle that around and get the molar mass here equal dRT over P. Now this version is very helpful, and this can help us to identify unknown gases. So if we can work out the density of an unknown gas, we can get to its molar mass, and that's helpful. So here we have a 10-liter sample that has a mass of 28 grams, and we're trying to find out which of the nitrogen oxides it is. So use that molar mass is equal to dRT over P expression from above. The density is the mass divided by the volume. There's D. Now we'll do R. Finally, the temperature here divided by the pressure. 1 atmosphere, because that's STP. Above, check all the units. We wind up with grams per mole as 62.757 or 63 grams per mole. So looking at the list of oxides we were given, the closest one is nitrogen trioxide, and so we guess this sample is probably mostly nitrogen trioxide with perhaps a little bit of one or two of the other constituents inside. So that's quite valuable being able to work out the density of an ideal gas, and that's about enough for today. Anyway, thanks everyone, and see you soon. Do have a look at the next 2 videos for more, and stay tuned for our next lesson, a short lesson, lesson number 24, measuring gas pressure.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.